So let's look at the strength a toroid has. First, we have three regions that we need to consider. One is the inside, one is in, another is outside. Inside, or this, I guess it's inside. This is in the toroid, and this is outside the toroid. Now, we'll make use of your Ampere circuits, Ampere loop, and the circuit law. What happens over here? Is there any current? Since there is no source, there won't be any magnetic field. What about this? Well, we do have a source, so there will be some magnetic field. What about here? That's the fun part. Here we have the source. Okay, let me do this actually. Now, this is the source, and this is the sink. For every source, there is a sink. Every source, there is a sink. It's a turn, right? It's a wire. So for every wire that comes out, there is a wire going in, and there's a lot of turns. Hundreds and thousands of turns. So in that case, what happens? Since the source and the sink are equal, according to our Ampere's law, the magnetic field line on this line, imaginary line, will be correct, 0, because the RHS will be 0. Okay guys, anyways, that will be our derivation as well. I'll show it. So let's start with considering an ideal toroid solenoid with n turns per unit length. Let I be the current through it. So this will be a diagram. We need to draw loop 1, loop 2, and loop 3 along with the solenoid. Okay, you have to make use of your compass and protractor, only then this will make sense. If not, this is decent, but it won't look good. So I missed out one thing, that is to show you guys how exactly the magnetic field lines within the solenoid will go around. Is it clockwise or anti-clockwise? In this case, it will be, no, it would be this. So it is, okay, in this direction, guys. Right? If you think about it, here we have to hold our right hand in such a way that it should be this way. So our thumb is pointing this way, and yeah, I think I didn't justify that. Okay, now I got it. Right? See here, our hand is going up, here our fingers are going down. So here you can see the current is going out, here the current is going in, this is out. So when you do this, the magnetic field lines, or the thumb is pointing in this way, and so the magnetic field lines are this way. And we can take our Ampere circuit law to be the same, that is same structure. Right here we are looking at from the top. So if you use your right hand rule, right, when you have to imagine the Ampere's loop to be something like this, so your thumb will be pointing inward. I'm not able to draw it well, so it would be something like this. Okay, so it would be something like this. Again, this is from the top view of your hand. So let me draw it properly. So that's your hand. Right, I've drawn a gloves view. So yeah. Okay, does it make more sense now? This is a better. So if I do that, my thumb is pointing downward and my current lines are going downward. So both will be in the same direction. So we need to recognize that the DL and B are in the same direction. It is so. Both are tangential, both are in the same direction. So the dot product on the LHS will be, yes, cos theta is going to be 1. That recognition is very important. So these are your Ampere and loop. So these are your loops, actually loop. And that would be your direction of course, in each case, direction of integration can change. But we'll see that it won't matter for loop 1 and loop 3. Loop 1 because there's no current. Loop 3 because for every current that is coming out, there is a sink. The source and the sink, it's an analogy that I made at the start. It's not from the books, okay? So please don't use that per se in your exams. It's only for discussion. Now, this is how the exact derivation looks like after writing the statement. So let's consider ampere loop 1 as shown in the figure. Then we need to write the law once. So this is where we'll write mu naught I enclosed. So there's no enclosed part. As the loop encloses no current, the RHS will be equal to 0. Consequently, in the magnetic field in the open space interior to the toroid is also 0. That is, actually that statement is enough. So basically we're telling this is 0. So the entire thing is 0. Okay. Right. That's it. That's about your first loop. Second loop. The second loop has to do with P dl mu naught I enclosed. Now let's consider our LHS. So whenever we know that there's a lot of work to be done, so consider part by part and move forward. So B is uniform over here. Entire toroid. First thing, so B is constant. The next thing is DL and B run parallel. So what does it indicate? So this indicates theta is 0. So if I substitute, therefore, LHS will be integration of B dl cos of 0. So B is constant. That is 1. So we have to integrate the entire dl, the entire loop, and this is 1. So if I integrate dl the entire loop, what happens? It will be 2 pi r. Right? We are just adding up the entire loop. So this is approximately not taken the radius, but yeah, it would be so. Okay, yes. So I should be taking this as r, but my diagram is bad. Too many things. So that's r. Now let's look at the RHS. It's always good to go part by part. So mu naught I enclosed. So the current enclosed will be how much? N number of turns into I. Have I written that it has n number of turns? No. So let's write where n is total number of turns. So let's substitute n1. So let's call this as 1. So this will be b 2 pi r mu naught ni. b 2 pi r mu naught ni. So when I transpose this, it will be mu naught n divided by 2 pi r into I. But this is the entire number of turn and this is the length. So what will it give us? It kind of gives us the density aspect. That is small n. And this is the same as your solenoid expression. Okay, right? Finally, exterior. So exterior, this equal number of current coming in and equal number of current going out. So all in all, your B will be, or let me do this, I enclosed will be equal to since equal number of turns are current is coming out, and say this is in, and so this will be equal to 0 ampere, and therefore our B is also equal to 0. So this is our entire derivation. So here it's not at all complicated. We have considered 3 ampere loop. So the inner one has no current, so RHS is 0. Outer one has equal number of current coming in, going out, so RHS is 0. Only the middle one I have to consider with radius R. So that's the only thing I missed out initially. So if that is the radius R, then our integration for the inside the toroid looks like this. B is constant. DL and B are parallel to each other. And so your LHS will look like this. So integration of the entire circle, that is basically circumference of the circle, that is 2 pi r. And so when you equate it and solve it, and we end up with the answer that we saw.